We're starting with a Ask Science question from Reddit from user, I think it's Slystone, Slystone, SLYST0NE.
Mm-hmm.
And the Reddit user asks, if my 60 gigabyte phone is full or empty, is there a difference in weight at the nano level? Yeah, I think that's an interesting question. I think like we've all kind of heard, or a lot of people have heard different versions of this question. But I want to get a little more specific with it. And I think, well, like, because I was trying to talk this over with some people and we were kind of running into different ideas and thoughts about it. So I think the easier thing is to like rephrase this question first and try and get it like with the heart of what I think the person's asking.
Okay.
So like, I think kind of in general, what they're asking is like, does data have weight? Does memory have weight? And I think for us, I think we should focus on like the most common form of memory that we see in our daily lives, which would be like an SD card, USB stick, or SSD, flash memory.
Some sort of like solid state memory.
Yeah.
Not a platter drive, not like tape or something like that.
Yeah. We can talk about like hard disk drives or something. And I think that's also an interesting one to cover, or same with like magnetic tape. But, we all, well, at least in the United States, we all have phones pretty much. And we all have computers, and this is just the main form of memory in all of that. At least in 2018. The reason I want to take the whole phone out of it is with a phone, we kind of end up getting a full system of things that we have to consider. And, like the battery and the energy and that sort of thing. And I kind of wanted to just separate the memory system from everything else. So that's why I was thinking it's probably easier to talk about an SD card first.
Right. I see. So is an SD card, they said 60 gigs. I don't know if the amount of data matters, but let's say, some size SD card is empty. Does that have a different weight than if it was full?
Yeah. Or mass, maybe?
Yeah, I know. I hesitated on that word, but I think we're going to assume it's on Earth. So if the mass changes, the weight changes. We could work out what that is.
Right. So I think if you've never studied physics or anything, you might ask like, how does this question even make sense? Right. I have a feeling like you could answer that question. Like, why is this a valid question to ask? Why would we even try to answer it?
I don't know. You asked me, or you alluded to the fact that you wanted to talk about this on the podcast a while back. And I told you, I saw the question and I clicked on it, but I didn't read all the answers. But I did see that the first, like, most upvoted answer was not what I thought. It was the opposite of that. So, yeah. My initial thought, it's a yes or no question, and my answer is no, it doesn't change mass. But I could be wrong. I don't really know.
So why wouldn't it change mass?
I don't know. It's you're flipping a bit. So like, does your light switch change when you, like, the mass of your switch change when it's in the up or the down position? That's how I'm interpreting it. And I realize there has to be some electricity that flows to actually make it a 1 or a 0, and maybe the electrons being stored, but it's still part of a circuit. And I don't know that there's any like capacitance that would actually lead to more or fewer electrons being within. Like it should still be a neutral device charge wise.
Yeah. So I think that's kind of the heart of the matter. I think that's where it gets, where it's interesting when I started looking into it. Because I think there's kind of two ways we could potentially add mass, right? And that's through adding actual matter, like you were suggesting, like electrons or something else, or potentially energy, since Einstein's equivalence principle,
right? And I still I'm processing something in my head, but just quick thought is that I don't know what the difference is between a bit being a 0 or a 1. And are we taking into account thermal energy? Because that's going to dissipate eventually. Like, is this like what's the word I'm looking for? Is it an equilibrium? Like, has the bit flipping happened, and now we're just let this thing cool off to whatever temperature it is?
Yeah, I think
after
so.
It's been sitting for a long time. We're not taking into account like resistive heating because of all the current that goes into flipping all the bits. Right?
I'm not. No.
Yeah, because it definitely will warm up when it's initially being flipped. But and everyone has a thumb drive. They can do this. Like, write a bunch of data to your thumb drive. It's going to warm up a lot. That USB port gets really warm. But I don't think that's what they're talking about. It's like the steady state, the equilibrium state.
Right. Yeah, I think that's it. And you're kind of like, you've alluded to a few things that I think maybe we should go a little more in depth on, talking about bits and ones and zeros and that sort of thing.
Yeah.
So in general, I think it'd be useful to talk about, what is memory? How is it stored? And, you and I both know data, we store it in a binary system. That is, we usually say it's a 1 or a 0. And that's it's really just the abstract notion of a physical thing.
Right.
And a 1 can mean a lot of different physical things, and a 0 can mean a lot of other physical things. So this is just an abstraction, and then we'll get down to the specific of an SD card.
Good. I might need help on that because I'm not super clear on it. I know I've looked it up and I've seen so many YouTube videos, but I guess nothing's ever stuck enough to where I could say how it works exactly at this point. So
yeah,
we'll see what you say.
Yeah. So data stored is 1s and 0s, and then the kind of the unit or the cell, I guess, that can be the 1 or a 0. I think that's usually what we'd call a bit. Right. So just for everyone, there's like a bit is a 1 or a 0, and then 8 bits is a byte. And, then from there we get to all the stuff that we know, like our 60 gigabyte SD card that we're talking about is really 60 times a billion? It's giga.
Yeah, billion.
60 times a billion times 8 bits.
Yeah, that's a lot of data, obviously, and such a small thing. Like, what? It's got to be on the scale of atoms, or maybe a few atoms. What? So remind me, what is in the SD card that's actually storing the memory? It's a transistor of some sort, right? Like, it's something that is flipped on or off with voltage. But what I don't really remember is how it saves that after the voltage is turned off.
Right. So you're getting just a hair ahead of me.
Oh, okay. Sorry.
No, it's fine. Yeah. You're seeing where I'm going.
Yeah.
And if this wasn't a podcast, I would just jump there with you. But
all right, let's take the listeners on a journey.
Yeah, I've promised friends this podcast for a while, and I want to let them go on the ride.
Okay, cool.
So yeah, you're since you already understand a lot of this, you're kind of jumping down the road, but it must be right. So we have a bit, and we must physically store this information somehow. Like on, off, up, down, left, right, charged, uncharged, something like that, where it can only be this thing or that thing. There's no in between with these things. And we have to do that in a physical thing. So like a hard disk drive is magnetic spins, right? Like domains really on a drive, but it's a little different and that's just one example, one way we could do it. And then the other thing, so in order for this to be memory, it has to be binary like that. And then it also has to last a long time, at least this type of memory, an SD card, right? You don't want it to be, when you unplug it, it dies like your RAM does. Or you don't want to, you save all your data on there, and then a year later you come back and you put it in and it's all corrupted because it didn't last, right? So those are kind of the two conditions. It has to be binary and it has to last a long time. So how do we do that?
I'll add a third one.
Oh, yep.
In that it has to be rewritable. Like, you have to be able to erase it and rewrite it essentially infinitely many times.
Yeah.
Because I mean, I could make some solid state storage with stones and a hammer and chisel, but that's not going to be useful.
That's
to be
true.
Rewritable.
That's very true. Yeah.
Yeah.
Okay. So what do we have? We have binary system. In order for it to be a bit, it has to last a long time, and it must be readable or writable and erasable and readable.
Right.
Okay. So the SD cards, they use FETs. Now this part, I have all this information here, and I feel like this is where you can kind of jump in and
sure. I do know a little bit about solid state devices. Probably not as much as I should, or as much as I would like to, because I do always have to look it up. I forget. Yeah, FET, field effect transistor.
Right, and so I have essentially a bunch of like very high. When I say high, I mean like more on the abstract level, not deep into the physics stuff here. And I feel like I tried to think of good like analogies to kind of like have it make sense. I didn't come up with anything great. So I think that's where you're going to be.
So can I talk about a transistor, and then you jump in and steer me towards the field effect and like memory storage part of it.
All right, please do.
So a transistor, if we think of not solid state, but the old like valve, as the British would say, or tube, like amplifier stuff that we have, basically it is something that is put to a really high voltage and warmed up. And we talk about a piece of metal warmed to the point where the electrons literally boil off. Like this piece of metal is so hot, it's just leaking electrons into the air around it. So it's boiling electrons off. Those electrons, they kind of repel each other, but they wouldn't really go anywhere without an applied electric field. And that electric field you set up with an opposing piece of metal at a different voltage. And so all these electrons boil off one piece of metal and then fly through space like a little gap into hitting the other piece of metal across a tube, like a vacuum tube. So it's an evacuated chamber. Electrons are flying from one needle, essentially, that's really hot to another needle. And that's just a current. So you set up a circuit with current flowing through the air. What you can do is set up an extremely small signal, a really small voltage in the middle of that. And that is connected to like a screen. Imagine like a metal grate or like a small metal screen in between the two needles. So there's electrons flying through the air, and then you put a screen in the middle, and you can apply a voltage to that to either attract the electrons so it won't reach the other side of the other needle and complete the circuit, or it won't attract the electrons. They fly through the gate unimpeded, essentially, and do complete the circuit. So that's your 1 and your 0 state, is apply a little voltage to a screen, and then that big voltage that's flying through the air, the signal that you're applying to the gate gets amplified. So if you're sitting here with a guitar and it's sending a signal that's pretty low, not a really loud electrical signal, to the screen that's in between the two needles, that signal from the guitar gets amplified by that huge current that's flying through the air. So every time a string goes up, the voltage on the gate goes high, and that attracts the electrons and prevents the current flowing through the circuit. And every time the string goes low, it turns off the voltage to the gate and lets the current flow through. So if a string's going up, down, up, down, up, down, that frequency gets transmitted to the electrons going across that air gap, and they're going to turn on and off, on, off, on, off. And that's going to be your basically your tube amplifier. But that's all not solid state. That's all like basic electronics and vacuum tubes and these glowing kind of look like light bulbs inside a guitar amp. But that's a transistor. That is what it is. Now, getting into solid state, what I understand is instead of electrons flying through the air gap between two, really hot needles, essentially, you have a semiconductor that has the ability to let electrons travel through it, but you need a way to turn that electron transferability, instead of using a technical term that I can't think of right now, conductivity, I guess. Instead of letting the electrons move through the semiconductor, what you do is you bring in another piece of metal and touch it to that semiconductor And that will essentially act like the screen in the air gap, and it'll either turn up the conductivity and let electrons flow, or turn down the conductivity and prevent electrons from flowing. And it's the same thing, a really low voltage on that little piece of metal in the middle of the semiconductor can be amplified to a large voltage or current flowing through the semiconductor, on, off, on, off, on, off. That's just switch. So that's basically a transistor like amplifying a signal. And so here's where I need you to jump in and say, how does that lead to memory?
Right. So just before we get there, I think I'm going to add in some terms here that might help as well. So yeah, there's 3 parts to this type of transistor that we're talking about. There's a source, a drain, and a gate.
Yeah.
Which I think, so like the source in your example is, the piece of metal that's boiling off the electrons.
Mm-hmm. The drain, that's the source of the the electrons.
The drain is the other end where the electrons are going, where they're ending up. Mm-hmm. And the gate is that thing in the middle that's allowing them to go through or not go through.
Right. Yeah. So, perfect. And it gets more complicated with the semiconductor in that they're not just electrons. There can be holes. So there's different charges. Instead of negative electrons, it could be positively charged holes that could be flowing. So I don't want to just say the source is where the electrons come from, because that's not necessarily true.
Right. Yeah. And you can actually have transistors that flow from drain to source as well. Mm-hmm.
Okay.
So, I mean, generally, I think the right term to say is you have one end where you have a charge carrier that moves to the other end. And then there's a gate in between that's allowing that charge carrier to move or not move in between the two. Mm-hmm. For the sake of consistency and just, keeping it on track, let's just use source as the charge carrier source, and we'll just pick electrons. And then drain as where the electrons end up. But just know that, it can be positive holes or it can flow the other way. But for just moving on, we'll talk about source is the source, drain is the drain, and gate is the thing in between.
Cool.
So in that current setup, you can't have this non-volatile memory. That's not enough to do what we want. I mean, you said we have the binary system now. We have the on-off ability. Right. Whether that gate's open or closed, we can think about it maybe as.
Yeah, but I should add, it's not strictly binary. It is analog. Like you can get your voltage. Your amplified signal can go between 0 and 1, and you can get a half. Because that gate attracts some electrons, not all of them. Some would still get through. So it's still not quite digital, but you can see how it could be digital if you're just your instead of a guitar string going up and down, you apply a voltage or you apply no voltage, and there's your digital.
Right. Yeah. I think a lot of times, it's once you reach a certain threshold of current or voltage, that's when you say, okay, now it's on. So you might have a little bit of leakage, or not just leakage, but it might be on a little bit, but we'll say, we're not going to count that because it's not enough. It's like we're not purposefully doing it.
Right.
At least in this application. There's so many more applications for FETs than what we're going to cover. But
so I should add the FET, the field effect transistor. So I described the transistor like the valve, the tube, but the field effect thing is put a little piece of metal in the middle of your semiconductor. The electric field that piece of metal produces when a voltage is applied to it, that affects the electrons flowing across the semiconductor. So it's like the electric field penetrates into the semiconductor, so that electric field affects the transistor or the semiconductor part. That's your FET.
Yeah, it actually for your enhancement type FET, when there is an electric field present is when you will form this channel and you'll allow electrons to flow from source to drain.
Okay. I kind of remember that. You like push things away and then it opens up space for the electrons to flow.
Exactly. Like you'll create you have essentially two. I mean, to get a little technical, the body is made up of a P channel, P doped, not P channel, P type,
P type, yeah,
silicon, and then you have two areas where the source and the drain are that aren't connected, of N type silicon, and then the gate sits in between them. And when the field forms, it pushes holes away from it, I believe.
Right.
And then that connects the two N types together and allows electrons to flow through them.
Right. That's right. It's all coming back. It's been a long time.
So typically, I think most FETs that we see now are called MOSFETs, which stands for metal oxide silicon?
Semiconductor. No, metal oxide semiconductor.
Yeah, field effect transistor. So what that just means is, between the body and the gate is a tiny layer of metal oxide. I think it's usually silicon dioxide. That's
not a conductor. It's like a little insulator gap between them.
So electrons can't jump to the metal gate. So what they developed to make this solid state flash drive is what's called a floating gate MOSFET, and it pretty much looks exactly like a MOSFET, where there's the source and a drain and a gate in between, except there's not just one gate but two stacked on top of each other. And so you got to imagine. It's the body. And this is where it gets technical, and I feel like there's probably a good analogy that we might be able to come up with. But so it'd be the body, and then a layer of this silicon dioxide, this insulator, then a piece of metal called the floating gate, and then some more insulator, and then the control gate, which is the control gate is essentially the normal gate that we've been talking about so far.
Okay.
And to give you the quick, let's jump to the end. We can talk about how it all works. Is what happens is there's a way through. Usually, I think it's through hot electron injection or hot carrier injection. The electrons, when they're moving from source to drain, you apply an electric field on the control gate that pulls on the electrons. So as they're traveling from the source to the drain, they're kind of getting pulled towards the gate.
Okay.
And they'll actually tunnel through the thin metal oxide layer, the insulator, and jump onto the gate, the floating gate. And it's called floating because it's not connected to anything. It's completely surrounded by insulator.
Huh. So it's all quantum mechanical. Like the electrons literally quantum mechanically tunnel.
Yeah.
There's a chance that they're going to jump across that gap and then they're going to get trapped there.
Yep. Which kind of blew my mind that in this everyday thing is quantum mechanics.
Yeah. How come they don't tunnel back out? What keeps them stuck in the floating gate?
It's because you're accelerating them from source to drain really quick. So they have to pick up. It's hot electron injection, and hot electron. These aren't actually hot things. Like if you touched it, you'd be like, "Ow!" It's hot, meaning it has a lot of kinetic energy. It's moving fast.
Yeah. I think I kind of remember talking about that, they're ballistic electrons, you just literally just fire them into the semiconductor from whatever piece of metal that's making the circuit. I kind of remember that stuff.
I think it's along those lines. But as they're traveling, so they have all this speed, you apply an electric field that pulls them up as well. So they have some probability now because they have all this energy of tunneling. They're essentially, you've raised their energy level. So, and then
once they tunnel through, their energy drops dramatically. They're no longer hot electrons, and so they're just going to be sitting there trapped.
Right. So you do this for a certain amount of time, changes depending on who makes the SD card and all that sort of stuff. But essentially, what you do is you pile a bunch of electrons on this floating gate, and now they just get stuck there. It's like it's a little electron pool. Mm-hmm. And now when you apply the voltage to the control gate to let the electrons flow from source to drain, that voltage gets screened by the electrons on the floating gate.
Okay.
So that voltage never actually reaches the body to make the channel.
I see.
So whether that floating gate is charged or not tells you whether or not there's memory there. That's your bit. It's if it's charged or not charged.
And that's how you read it, is you run electricity past it without the, I forget what the names of the gates, but without the gate there that's going to attract the electrons. Say it's empty. Say that little reservoir is empty. Mm-hmm. It's possible that electrons could tunnel in there, but you're not giving them a reason to, because you're not applying that other voltage to move them into that channel.
Right.
Is that right?
Yeah. So they'll just flow from source to drain like normal. And then when you see that current come out the other end, you go, oh, okay, I am. That's actually when the gate is when the little well, the reservoir is not charged. That's a 1 because you can get current through. Okay. And then when it does get charged, you cannot pass current anymore because the electric field won't reach. So the field effect doesn't reach the channel, and so it never opens up, and so you can't pass. So you try to pass current through, and you go, "Did I get any?" And it says, "No." Okay, that's a 0 then. Right. And then because you have this chunk of metal that's surrounded by insulator with these not hot electrons, they're stuck there. They can't go anywhere. Right. So you can come back in 10 years and plug it in. And, they're still there. And so when you want to clear it or rewrite it or something like that, change a 0, which means electrons are in the little trap, to a 1, which means get rid of the electrons. You just apply a big electric field and it kicks them all out. Is that basically how it changes? Yeah, you apply a big electric field and it's called Fowler-Nordheim tunneling. I remember those terms. Wow. Yeah. Been a long time. Yep. And it'll quantum mechanically tunnel through the oxide layer back into the body and, get absorbed into the material. And now you can, essentially the electric field will pass through the metal again. The floating gate. I'm looking up a textbook I used to use when I was a grad student, and it was a really good one. And it explained all this stuff really well. And obviously not well enough for me to remember it, but it's in there somewhere. Right. So, to go back to the original question, or maybe we could just we can answer the question and maybe review if we need. But to go back to the original question, does your 60 gigabyte phone or SD card, is it heavier or lighter when it's full or empty? Well, I mean, it depends on what you mean by full and empty. To get in a little more technical detail, because really when you write data, it's not all 1s or all 0s. It's some combination of 1s and 0s. But essentially, is there a difference between the SD card being all 0s or all 1s? And the answer's got to be yes, because you're adding electrons to the system. Got it. Okay. So there it is. It's a little bit more massive because there are electrons that weren't there before, and those electrons have mass. Huh. Yeah. And I tried to look up, what the charge is that you had to put to screen it, so I could figure out how many electrons are on that floating gate. And I couldn't figure out that information, because otherwise then we could have calculated, how much heavier is it? Right. I found the textbook that I used when I was a grad student. There's 2 authors. The main one is Streetman, like Streetman, Streetman, and Banerjee, Banerjee, Solid State Electronic Devices. It was a good book. It was accessible. You probably needed to take quantum mechanics, and then you could thumb through this book and get a lot out of it. It wasn't too difficult. It wasn't too technical. It was a good, probably late undergrad textbook, but I think it's for electrical engineers, and I didn't get into that stuff until grad school. So good book. 2 thumbs up. Yeah, I got a little bit of it from my book, Solid State Physics with Cattell, but
Yeah. I had a Cattell class, and it kind of touches on this stuff, but this Streetman book is a lot better and goes into a lot more detail about devices in particular, rather than just P and N type and then, the junctions, and that it kind of stopped there. I mean, it talked about some different things, but yeah, this book was better. Yeah.
So on a very high, I feel like high is the wrong word. When I say high, I mean, I'm looking at it from really high. I'm seeing not a lot of the features of something. Mm-hmm. So from a high level, that's essentially, the answer to that question, at least for an SD card.
Right. So it's not a neutral device. Those electrons came from the wall outlet that then connects to the computer, or I guess charges the battery and then goes into the computer through the USB port or SD card reader.
Right.
And into the thing.
Yeah. So that's why I wanted to abstract the SD card out of the system. Because I think if you said, does your phone change weight? Mm-hmm. I think the answer is no, because those electrons are in the battery. And then they go and they get stored in your SD card.
Right.
So, the whole phone, I don't think, at least in terms of this electron loss or not, doesn't change weight.
Yeah.
The charge of the battery probably does, but.
Right. So I guess we could say the mass of the universe doesn't change. Charge is conserved. The charge came from somewhere.
Right. Yeah.
But my wrong reasoning for saying it doesn't change was because I was kind of imagining these FETs were like a light switch, like the charge moved from one part of the semiconductor device to another part of the semiconductor device. I couldn't remember where, from where to where, but that was what I was thinking as to why the answer was no, is that it's all the same amount of charge. It's just getting moved around like a light switch. It's just either in the up position or the down position. The switch itself doesn't gain or lose anything.
Right. Actually I have two interesting thoughts to go off of that. One is, I do think, if you were to answer the original question, I think you're dead on because of that very reasoning. Your phone is just moving electrons around. They're not.
Right.
And I mean, honestly, if you put your SD card in your computer, your computer essentially isn't really changing mass, but it's when you take it out of it, that you've now separated it from the system. So that's why I wanted to isolate that system so we can focus on what happens on it.
I could answer it really easily. Your computer's heavier because it has an SD card in it, and then it didn't have that before.
Right, yeah. But along the same lines, though, talking about not changing mass at all. And I don't have a whole lot of info on this, so we could just spitball if you want. I think there's a interesting thing to be discussed with hard disk drives.
Okay, I have another place we could take this, which is kind of an abstract thermodynamics place. But let's go with hard disk drives. Yeah.
I mean, we don't have to go too far into it, but can you essentially explain, okay, now that you know you already knew, but now that we know what memory is, can you explain how a hard disk drive works? I'm assuming you already know some background there.
It's a little magnetic bit that it's like a record player with a needle, but it's magnetized, and then once it crosses a little place that it wants to write 1 or 0, it applies a pretty strong magnetic field, and it flips the little magnetic domain on that area. And then if it wants to read it, it just applies a lesser magnetic field, and it figures out if it's attracted or repelled from that area to see if it's a strongly magnetized region or not.
Right.
And that's basically my understanding of it.
Yeah. So essentially you have little regions called domains that are magnetized, and they can either be just, for simplicity, up or down. And that's your, up could be 1 and down could be 0, something along those lines. So I guess kind of the question, at least the just to score the surface of it for you is, okay, is it changing mass or weight? So I guess, okay, does it change weight? Is there a way that it changes weight while you're doing this read-write process?
I don't think so. It's just flipping the polarity. It'd be like, now it is actually a light switch or a bar magnet. You're just making it, instead of oriented in one way, you grab it with your hand and rotate it on the tabletop, and now it's a different way. So It was a 1 with its north pole, facing this one wall in your room, and then you grab it and rotate it, and now the south pole faces that wall of the room. It doesn't change mass, it's just rotated.
But what if I had 2 north poles and I tried to bring them close together, right? Because you're not just flipping you are flipping a single bit, but that bit's part of a system. Mm-hmm. And so,
the neighboring bits, you're making it not happy to be in that situation, and you're kind of holding it there.
Yeah. So I think a simple model that kind of discusses this, and I don't know a whole lot about, is the Ising model.
Yeah. So Ising model, from what I remember, the Ising model is there's different dimensions. So let's go one dimension because it's easy. Just imagine a string with a whole bunch of magnets evenly spaced on this string, like bar magnets. And you can imagine North Pole is repelled by other North Poles and attracted to South. So if you put a magnet next to another magnet, it wants to be flipped opposite. Like it wants to have a North Pole next to a South Pole. So adjacent magnets would line up. The ideal way would be alternating, north up and then south up, because they want to be attracted and close to each other, which is what we would call antiferromagnetism. So if something's a permanent magnet, it's going to have all the north pointing in the same direction in that long string of magnets, and that's generally not favorable energetically, but there's some situations where it is. So that's when you get those permanent magnets, when they have those situations. And then, you can extend the Ising model into like a 2D sheet with magnets in a grid, and then same thing, alternating is the preferred orientation. And then if everything's pointing in the same direction, it's not generally happy. It wants to flip every other one to make it more stable.
Right. So okay, what if we had I like the 1D case, it's easy to imagine your string of magnets, right? And whether when you walk by, whether it's north end towards you or south end towards you is your 1 or your 0.
Right.
So let's say you had them in the low energy, their preferred state, you were saying, where it was north, south, north, south, north, south, north, south.
Right.
And so on. Okay, but what if you flipped one, or you flipped all the souths to north? So now it's north, 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 north. Right. Is that changing the mass?
Well, I mean, I think there's some energy stored in there, so I suppose through Einstein, yeah.
Right. That's what I don't know too much more than that, but I think like, if you want to get highly technical, I think you got to say, because the energy levels of that little system has gone up. Mm-hmm. It's in a higher energy state.
Yeah, I think that's true. So in some way, it gained mass, not through any additional matter like the other situation, but just because of the increased potential energy, stored energy in that system. That stuff wants to get released somehow. Something's holding it up. So yeah, and I think that could be like a whole nother conversation, or you could probably just look up any YouTube video about Einstein and you will learn about that. Right.
Why that's the case.
Right. So is a scrambled hard drive less massive than a zeroed out hard drive?
Or I think it'd be the other way around, right? Scrambled would be, oh wait, no, you're right. Yep. I think so.
I don't know if you can alternate the bits. Yeah, that'd be tough to do.
I'm sure you could like write a program somewhere that does it.
Right. Yeah.
It wouldn't be like you normally saving data. Mm-hmm. And I think that's kind of a whole computer science thing, like we haven't really talked about. But when you actually fill up one of these drives, is you are essentially making it. Probably. I mean, I don't know for sure, but I'm going to guess it's probably roughly around half ones, half zeros.
Yeah, that's the most likely situation.
And then you're going to change a bunch of files and it's going to be completely different. You erase some, you add some, and it's probably still, if it's full, half ones, half zeros. So, it depends on, I guess, what the empty state was. But I think these whole conversations, we have to talk about these extreme cases where we turn everything into ones or zeros or have it perfectly mixed.
Are you familiar with Maxwell's demon? Do you know what that is?
Not I'll say what I remember of it, and then maybe you can fill me in on everything. But it has to do with some sort of boundary, right? Where you only let certain, I think maybe energy particles through or something, and you could potentially cool something really cold or something along those lines.
Kind of. It was Maxwell of Maxwell's equations, who studied a lot of thermodynamics and statistical mechanics, looking or thinking of a way to violate the second law of thermodynamics, which is that entropy always has to increase. Otherwise, you're expending more energy than you're getting out to not have that happen. So he imagined a box of gas, and you can imagine just the air molecules inside moving around at various speeds. Some are fast, some are slow. If all of them all of a sudden get faster, that's going to warm up the gas. And if all of them get slower, that's when the gas is colder. So what he imagined was this demon, he called it Maxwell, or he called the demon, and now it's called Maxwell's demon, that watched the molecules. And it could somehow, had like a radar gun and could pick up the speeds of the molecules as they approached some barrier in the middle of the box of gas. So like a little door that the demon controlled. And if he saw, say, fast molecules moving from the right to the left, he would let that through. And then if a slow molecule was coming, he would close the gate real fast. And in whatever, fancy way you want to imagine that he could do that, it's just, let's say it did that. So the rub is, if he keeps doing that and watching them, and fast ones get through, slow ones don't, they hit the wall and bounce back, you all of a sudden have a situation where there's a whole bunch of fast molecules on the left side because they came from the right to the left, and then slow molecules are stuck on the right side. And so that means that the left side's hot and the right side's cold. He's just separated the gas and made it into an entropy state that's lower than what it was before. Decreased entropy with no energy involved. Ideal gates, just as best you can imagine, ideal situation, whatever is powering his molecular speed reading abilities, no energy expended. He's just letting ones through and then other ones not. And then all of a sudden you get a lower entropy state. So what's the rub? Where did the entropy not actually go up or go down, or was energy actually expended? What do you think?
Well, I mean, if you have some sort of, well, okay, wait, before I go off, isn't this essentially kind of like laser cooling?
I don't think so. I mean, I guess because that's like atoms coming towards a laser, being Doppler shifting the light from the laser a particular way, and then you're leaving them behind. No, because that physically requires cooling with energy. Like a refrigerator separates hot and cold. That's fine. It doesn't violate thermodynamics. It's just you're spending energy to do that. Like the universe's entropy doesn't change.
Right.
Or sorry, it continues to follow the second law.
Okay. Well, I mean, I don't know. I feel like does a demon creature, if they're opening and closing a gate, isn't that going to have to take some sort of energy to do that?
I think the original thought experiment was that it didn't. It was just an ideal situation, however we can imagine that. I don't know what, but that is not the solution. There is a solution, but it's not that. The solution, so by the way, second law is not violated. There's something else that needs to be taken into account which Maxwell, I don't think came up with the answer. I think it took a while for someone like 50 years, 70 years until someone figured out what the actual issue was and how, and figured out a way to resolve this.
Okay.
And to give you a hint, it leads into us thinking about energy changing with storage memory in a way.
Yeah, I mean, nothing is, statistical mechanics is my worst subject by far.
I mean, it's not really, like, you don't have to know a lot to answer this question, but this is where it came up, at least the first time I heard about it.
I mean, isn't there's some probability that a gas could go into that state naturally? I mean, not likely, but it could.
It could.
So if it happened naturally, yeah, I could see, okay, well, why would it be violating any physical laws? But yeah, I haven't a clue. I mean, I could throw out other random, stat mech terms, Gibbs free energy or
no,
energies,
nothing like that.
I have no idea. Like, I couldn't.
The rub is that the little demon character, he has to be recording all this stuff. So he has to keep track of what's happening. And that is the increase in entropy that's counterbalancing the decrease of the gas's entropy. So basically, Shannon, have you heard of Shannon? The engineer, Claude Shannon, I think. He came up with the concept or worked out the details of information entropy, information having entropy leading to a measurable amount of entropy. So the demon keeping track of all this stuff is increasing the information entropy. Meanwhile, the gas itself is decreasing the thermodynamic, what we think of as classically thermodynamic entropy. So the fact that he has to log all this stuff and keep track of it, that's where all the entropy is going, essentially. So does that help us think about just information abstractly leading towards an increase in energy? And then, as we said before, making more mass because it has energy? I don't know. But I thought it led to the same. My mind went there when I first read the question. It's like, are we getting into that kind of question of like just the information entropy is now leading to energy being in the system that wasn't there before? Yeah,
I mean, that's probably a really great question that I'd have to talk to someone smarter than me about. Yeah, I mean, because does information have energy, or like, does data have energy in the first place? I feel like kind of you got to say, well, I'm thinking of like back to your stone idea. You can carve, get a chisel and hammer out and carve some information in stone, but it's not like that stone has, I don't think it's gone up in energy in any way. I mean, or like if you have a white blanket, and then you someone makes a white blanket and someone else sews, or I don't know how you make blankets. What do you do? Crochets intricate pattern into the blanket, and there's some like information in the pattern. Like, I don't think there's an energy difference between the two blankets. Yeah.
And I think it leads to the risk of conflating entropy and energy, which I don't want to do. And I don't really know the answer to that, but that's at least that's what I was thinking about when I first read the question. If that's what the person meant, or if that's where the answer could come from, was thinking about something about information entropy.
Yeah,
here, think about this. Let's go back to the refrigerator. It decreases the entropy of the system, like being the refrigerated air and then the room's air, right? It separates cold and hot, where if you just had a fridge open for a long time and off, the air in the fridge and the air in the room would be the same temperature, but then close the door to the fridge and turn it on, all of a sudden you separate hot and cold, just like Maxwell's demon. But we can look at the pump and the coolant and all that stuff and be like, okay, well, it took more energy than we're pulling out of the hot air inside the fridge to make that happen, right?
Right.
So the whole energy of that air of the fridge, air of room system went up. And I think we could say the same about Maxwell's demon, as long as we take into account the fact that the demon had to record all the information that he had to make it happen. So I think the energy of the system goes up by the entropy goes down due to energy being put into the system. And that energy comes from the demon doing the recording. The information entropy counteracts any decrease in entropy of the gas. And I guess the equivalent would be like thinking about the fridge. The entropy of the universe still goes up, even though inside your fridge in your room, it goes down because it came from electricity. The electricity came from, burning coal or something like that. So we get into the abstract, like how many layers removed is the entropy increasing? Maybe it's a few, but it still has to go up overall somewhere.
Yeah, right. Like, I think that's a common thing that people miss with the second law is the entropy of a system can go down. That doesn't violate the law of a. I don't know if the system is the right word of a single like unit.
Right. You can draw a boundary and have the entropy inside that boundary decrease. It just needs to increase somewhere that's in connection with that boundary. Like it has to go up somewhere else due to an interaction with that system.
Right.
Somewhere. It had to go up somewhere.
Yeah. So I guess, if you have your system, the thing you're looking at, and the environment, everything else, the entropy of your system can go down, but then the entropy of the environment has to go up more than the entropy of your system went down. Yeah.
Right.
So somewhere it's always going up.
So I think to recap, basically the solid state device gains mass because electrons are added to it. Like physically more electrons are on your flash drive when a memory is being written to it. So it's more massive, or its mass changes, at least whatever it thinks a 1 or 0 is. But its mass actually changes due to more or fewer electrons. And then a platter drive, magnetic drive, disk drive, changes its mass because of the increase or decrease in potential energy between the magnetic domains. How they're arranged on the disk affects things just through the equivalence principle, with energy being stored in the system leading to a change in mass. And then the last bit, I don't know. I don't really know what the connection was between Maxwell's demon and the memory, except to say that information can be thought, like reading and writing information can be thought as an exchange of energy as well. So I think just in a fundamental thermodynamics way, writing information leads to a change in energy, which also leads to a change in mass.
Yeah, I think I think kind of from, if I'm taking away this correctly, is it any like real physical, observable, measurable thing based on Maxwell's demon and Shannon is will have some change in energy to if the information is changing. Is that what it's kind of saying? Like
I think if we're changing the entropy, that has to be due to some sort of exchange of energy. And the connection that Shannon made was that information is entropy. There is entropy associated with information itself.
I guess what
fundamentally.
But I guess what I want to clarify maybe, and maybe this is another podcast, but is what is information? Because imagine I found a book written, in Chinese, and it's filled with information, and to me it's useless. It has no, it's not information to me. It's scribbles because I can't read Chinese. So I don't think when we're talking about information, we're not talking about that kind of information, are we? I think there's we're talking more about like a
I think we're talking about binary information, which the quick definition, how many yes or no questions do you need answered to completely capture whatever you're describing? So say I tell you, I have a royal flush in poker. How many yes or no questions does it take to identify exactly what hand I have?
I'd have to sit down to think about that. But let's see. Oh, okay. I mean, I could ask you, is it hearts? And you'd say yes or no. Is it clubs? Is it spades?
Right.
Is it diamonds? I guess 'cause those are the only possibilities for that hand.
Yeah. So that would be 3 questions because, by the end, you don't have to ask the last one because you already know what it is. If I say no to everything and there's only 1 question,
right,
you got it, right? But you can actually do it in 2 questions. You can say, is it red?
Oh.
And then they would say no. And then you say, okay, is it spades? And then they say no. And then you know it's the clubs.
Right.
So that is 2 questions worth of entropy. Whereas if I say, I have a pair, how many yes or no questions until you get my hand of poker?
Right. So we can, get the same number of questions to get the suit. But then, now we have to ask all these questions.
Well, not only that, you have to get the 3 other cards also. Because it's the pair that's 2,
hand.
But to describe the entire state of the hand of poker. So for your Chinese book, maybe you don't know the best optimal questions. That was a great example because you said, I can do it in 3, but maybe someone else can do it in 2. So just because you don't know Chinese, somebody else could figure out the optimal questions to describe that book entirely in terms of yes or no questions. And that's the 1 or 0 amount of entropy of that book in terms of 1s and 0s.
I see. Okay. I feel like this should be a whole little podcast. I mean,
just entropy, episode on entropy.
Entropy in general. Yeah. Because I think that's a thing people don't really know about. I mean,
right.
A lot of physicists that I know don't have like a great intuitive understanding. I mean, I don't clearly of what entropy is. Everyone says, it's chaos or it's disorder, measurement of disorder. Yeah.
But I think your question of, what is information? I think that's that's a fundamental question of the universe that I don't think people agree upon. Or, some people think there is no quantum fields. There's, no gravity at the bottom of everything. It's just the information, the 1s and 0s. Like we live in a digital universe. Like that's it. I don't know. I don't even know what that means, but I know some people think about physics and cosmology that way.
Well, we should learn about it and tell everyone else.
Sure. Yeah. There's a good book. We can do some homework. I've read it and I probably need to reread it because I didn't understand it. But do you know who Max Tegmark is?
He's been on Sam Harris's podcast, I think.
Oh, yeah. Yeah, he's an interesting guy. But he has a book called Our Mathematical Universe. Or the mathematical universe. I don't know, something about mathematical universe. And he argues that at the bottom of everything physical is just mathematics. And he gets kind of into the information entropy of the universe kind of thing. It's a good book.
I definitely
need to reread it before I talk about it on the podcast because I didn't really understand it. So,
as an aside, since we're talking about books, I got to meet Sean Carroll the other day.
Oh, really?
Yeah.
Oh, that's cool.
Cool.
Nice. Where was that?
At UCSB, he came and gave a talk about how gravity might arise from quantum mechanics. I ran into him briefly the next day, and I was like, oh, what do I say to Sean Carroll? I have it was just like him and me in a stairwell. I was like, I gotta, say something. And I was like, is there any way I could get you to sign an audiobook? How do we do that? Because all I have is audiobooks of his. I don't have any of his physical copies.
Sign your phone or something.
Yeah. He was like, I think you should just buy one of my real books.
Yeah. Or was it you? Somebody told me they met Griffiths from E&M book and Quantum book and had the international copy from Indonesia. It looks like all weird brown pages and different cover. And they met him and had him sign that copy and he was not happy about it.
That's funny.
That wasn't you, right? That was somebody else.
No, it was not me.
Yeah. I got Shankar's autograph on his Quantum book when he gave a talk at Santa Cruz when I was there.
Oh, that's cool.
Spelled my name wrong, but that's okay.